Hi there, my name's Dean. I'll be giving you a short presentation today on a single degree of freedom free vibration. This is for Engineering Mechanics 2 Assignment D, so let's get into it. So what is vibration? Vibration is basically a mechanical phenomenon whereby a mass in a system oscillates about an equilibrium point. Vibration is typically unwanted. Engineers try to design systems so that to minimize this vibration as much as possible. This is vital in the design of various structures, vehicles, appliances to ensure forces within the body are kept to a minimum, so that structure, vehicle or appliance does not prematurely fail when in service. There are various types of vibration. We've got free vibration, which we'll be looking at today, forced vibration, and the multi-degree of freedom system vibration, which is basically how all systems work. Due to time constraints and for simplicity, today we'll only be looking at free vibration of 1 degree with and without damping. So all systems where vibration is needed to be analysed are very complex, but engineers make it much more simpler to analyse them as a basic spring mass damper system. In the single degree of freedom systems, we basically model the vibration as an equivalent mass damper and spring system, which can be shown similar to the one on the right, but in this case we're just doing it without dampening. So the system can only be moved in one direction. So when the mass moves to the right, that stretches the spring, which then in turn imposes a force generated to the left. As we won't be taking damping into account in this instance, the system will oscillate freely forever until imposed on by another force. And that'll have an equivalent mass and equivalent frequency, the natural frequency which it will vibrate at. Engineers use this to calculate various displacements, velocities and accelerations of the body to ultimately work out forces. So in this analysis, the free body diagram can be seen on the right hand side. So then we use Newton's second law in the analysis, so feel free to pause and go through the maths. So basically we have F equals ma equal to the spring constant times the displacement. Then when we can move that to the other side, then we've got a second order differential equation, which we can then solve for x. So that'll have a homogeneous solution, which we can go through, differentiate twice, and substitute back into the first equation. And basically we'll find lambda, then substitute that back into the original equation, and we've got pure sinusoidal motion, which is inevitably what vibration is. And by definition, the natural frequency that the body will oscillate is given as the square root of the spring constant divided by the mass. If there are more than one spring arranged in either parallel series, the equivalent spring constant can be figured out. So for parallel, we've just got the sum of the two spring constants times the distance the system moves, and in series we've got the 1 over the equivalent is equal to 1 over the first plus this 1 over the second. And these can be seen in the pictures below. In reality, there will never be a system which will continually oscillate with a sinusoidal matter at all, due to the fact that mechanical energy will be lost of the system, which is due to basically friction, noise, heat. This can be shown in the similar animation to the undamped system, shown to the right here. So basically, to model this damping effect, engineers use a viscous damper in the analysis to account for all these losses, and the force due to a viscous damper is given by the relation F equals the damping constant times the velocity. However, this is only an approximation, as viscous is easy to analyse, as opposed to the actual damping which will be going on in the system, which is basically dry friction and hysteretic damping. So the analysis is very similar to the free undamped vibration which we did just before, except there will be an extra term in the differential equation. So the analysis is very much like we did before. We're using Newton's second law, except we've got that extra viscous damper term. As you can see by the free body diagram, the force will be acting upwards as opposed to the motion, similar to that of the spring force. So again, we have a second order differential equation which can be solved for x using a similar method to before, so just feel free to pause it and go through the maths. But yeah, we basically find a solution, differentiate it twice, then substitute it back into the original equation. Then to simplify things a bit more, we use the relationship as of the natural frequency squared equals the spin constant on mass, and we define a new parameter zeta, which is 2 zeta natural frequency equals the damping constant divided by mass. So when we substitute all them in, it's a much nicer looking equation. We can find lambda easily. So using the quadratic formula, we can easily find lambda here. Now substituting that back into the original equation, we see that the displacement response has both a sinusoidal component to it and a exponential component to it. And we also define that the damped natural frequency is equal to the natural frequency times the square root of 1 minus zeta squared. And zeta basically determines what type of response the system is. So if zeta is less than 1, we've got an underdamped system, but that's basically going to oscillate and decay. Then when we've got zeta equals 1, it's critically damped, so it's purely decaying quite quickly. And then we've got when zeta is greater than 1, we've got overdamped, which is purely decaying. And in our analysis, we'll mostly be looking at the underdamped response, so that will have a decaying exponential part to the displacement, along with superimposed with the sinusoidal response similar to that of the undamped system, which we analysed before. Now to determine this zeta, we have to use the logarithmic decrement to find that, which is given below, which you basically have to read off a graph. So you get the amplitude of a number of peaks and put it into the logarithmic decrement equation, and the more peaks you take, the greater the accuracy of zeta will be. And that's pretty much all the theory behind the free response of damped and undamped systems. So we'll finish it off with an example. So in this simple example, the question asks us to find the natural frequency of the system, which is shown in the picture. So the free body diagram will look similar to this, just underneath the system. So we'll let x be measured from the unstressed position of the system. So the equation of motion then becomes ma equals spin constant 1 times the distance that it is going to move from the unstretched position, then minus the second spin constant time multiplied by the difference that it moves from the unstretched position. Then because it's on an incline, we have to add the weight force component, which is going to be parallel to the floor, and that w sine theta is going to be the strength length times the sum of the two spring constants. So once we put all that into the first equation, we'll find that the weight force component cancels out, and all we've got left with is just ma equals k1 plus k2 x. And then from the definition of the natural frequency, square root of k on m, we use the equivalent a, which was k1